Good morning, everyone. So, need to see. So this morning I woke up and saw this, beautiful snow outside. It's just magnificent. So hope you all enjoy the scenery. So coming from California, this is definitely a nice change of scenes. Right? So let me introduce myself. So my name is Zheng. I'm a director of engineering at Walmart Labs search team. Right? So I'm leading the search platform team. And what this team does is we're responsible for all components within search platform. Right? So this including all kinds of data pipelines, runtime, serving stack, tooling platform, what have you, right? So what we build, currently is powering both the Walmart.com and also the samsclub.com. So in today's talk, we're going to focus more on the data pipeline part, right? And specifically, we're going to focus on how Spark technology has helped us to meet the challenges of our platform scalability, increasing business demand. Anyway, so the way we structure this talk is two parts. Right? The first part, I'm going to spend a few minutes highlighting some of the challenges we're facing, and hopefully give you a context within which you can appreciate more about the second part, which is the more meaty part that Nirmal is going to address, which is the details of the concrete scenarios. So, and talking about challenges, I think this is definitely a very exciting time to be at Walmart search team. One of the reasons is that we have seen over the past few years exponential growth in our data size. Right? So this chart shows you the product catalog growth year over year. In 2012, if you look at the chart closely, you probably could not tell the exact number. We have less than 1 million product in our catalog, okay? And now in the year of, we're just past year 2016, we have 30 million, right? And for this year, by end of this year, the projection is we're gonna have somewhere around 100 million products, okay? So if you think about it, right, it's really, within a short space of 4 and 5 years, our product catalog size has increased 100x. 100x, right? So take that in. And this is not some, kind of POC system. We're talking about production system. Essentially, this put an enormous challenge on all our application stacks, right? So including data pipelines, runtime systems, everything, right? And things would have been simpler if this is the only growth. For the search engine to work properly, we have to crunch a lot of data, right? Tons of data, in order to produce, the needed relevant signals and all the other supporting data, either in the search index or in other kind of data stores, in order to have the optimal customer experience, right? So. And this slide shows you, all the other data that we have been using. The growth year over year for the last couple of years, and here you see that also the similar kind of exponential growth has been observed, right? And this slide is a very simplified version of our old search data pipeline, right? So this gives you a taste of what kinds of data we're dealing with on a daily basis. And here you can see at the center, there is a data collector, right? And we collect all kinds of data, from pricing data, from seller content, from there's also legacy product data, there's store pricing. So being Walmart, we have both online and the store. So there's also the store availability. All kinds of data is collected in one central place, and then we do a kind of data pool once a day to build a search index. We use Solr currently, right? So then this index was updated in the Solr, and the runtime stack also calls a microservice that gets real-time updates, right? For things like pricing, availability, to surface to the customer, right? So, however, I should emphasize here that it is a runtime call. It is not updating the search index for this real-time data. So this is the kind of the old data pipeline. Right? Now, what this data pipeline does not fully address, right? And over the years, we have this increasing business demand, which is the real-time processing of a lot of this data, into the search index. All right. And the reason for that, I can give you a couple of examples, right? For example, an inventory status, right? So inventory status, you could say, yes, you could pull it, at runtime and surface to the customer, everything would be fine, right? Well, the real situation is actually more complicated because sometimes you need to adjust your, product ranking based on inventory status, right? For example, if you search for some electronic devices, if all the popular devices, maybe let's say the top 10, products are out of stock, right? And you have, equally relevant products, but available in stock, right? So the natural thing to do is actually to show the product, right, the relevant product that's in stock, so that customer can actually buy them. Instead of showing the product, but then customer has to kind of either scroll down or paginate further to find the product that they can buy right now, right? It's just one example. There are many other kinds of data that would be really beneficial if we can incorporate them in the search index in near real time, so that they can participate in the deeper, algorithm of product ranking, not just, kind of displayed to the customer. Right? So, and here is the, the new search data pipeline we have built. And I would like to highlight two aspects here that addresses the real-time data needs, right? So the first one is that from the central place where we collect the data, now it's a kind of Kafka queue. And from there, we do Spark streaming. Essentially, we process the event update in real time, right? In real time. And then we update the search index in near real time. And of course, it's ongoing effort to make it, as fast as possible. And the second piece is this Spark streaming, for all of this real-time data that's into either the search index or the secondary storage, so that they can participate in product ranking, right? And things like, as I mentioned, availability, pricing, even product advertising information, right? So with this, right, you can see the complexity of our data, right? So if anything would like to take away, I think the challenges are maybe four main points, right? One is the scalability of the data, right? And the second one is kind of the real-time processing needs, right? And the third one is that also with this kind of complex data, there is also a need to do more in kind of anomaly detection, that kind of thing, right? And the third is also business use cases and functionalities. They're also increasing in complexity. So without further ado, I'm going to have my partner Nirmal come up and talk through the detailed use cases. Thank you.
Hello. Yeah, thanks, Jan. So I'll take you a little bit deep into technology. On how exactly, because this is just a very simplified version of the architecture, but there is a lot more going inside, which is so many data pipelines, which is like in hundreds of data pipelines that powers our search index. So, and how we generalize those pipelines, how we scale those pipelines using the data frames. So I'll try to give some code snippet also so that I can explain you better that how we did it. This is, the next slide is general stats, basically, this is how we are, our real-time pipelines and the batch processing doing, which is on the daily basis, like at one point of the time, we process close to 10,000 events a second for our index update, which is the merchant updates, inventory updates, pricing updates, availability updates and everything. And then we have a microservices. If you look at back on the yellow side, all the microservices, which we have close to 8,000 events per second updates that we get, and we process those updates on the real-time fashion. And then we have a analytics pipeline that we run. So we own, as a part of the search team, we own search and the browse pages of Walmart.com. So when you go to the Walmart.com, you browse products or you search on something, you type any queries, those are the two pages that we own. So any traffic that comes, any customer behaviors that happens on that, we process the data on the real-time fashion and generate the analytics like traffic across the region and category, like what categories are getting popular, so that our business can take care of it. That okay, if let's say electronics category is popular, people are looking at the electronics categories, let's give more discount or something. Let's make sure that our availability and inventory is fine. So those kind of things that drives from our Spark Streaming and custom Elasticsearch data loader. And then we have a custom jobs, Hadoop jobs, that we process close to 50 to 100 terabytes of the data at one point of time. And that powers all our signals, which is the relevant signals, which indirectly and directly impact the ranking of the product on the search pages and the browse pages. So those are a couple of. Now, I'm going to switch a little bit here how we use DataFrames to build all the scalable pipeline and the flexible pipeline that we build, that we have. And we have close to like 500 jobs that runs almost all the time to power the previous slides, the index pipeline. So what is data pipeline basically? So we have two types of data pipelines. One is that real-time data pipeline and the batch processing. So batch processing that powers all our analytics, data science, all the config, business logic, and everything which we offline process and make it available. Real-time processing, we have just shown you, that powers directly to our search index, which directly impacts the relevance of the product and the ranking and the re-ranking of the products. So if you look at the data pipeline, this is the component of the data pipeline. There are 5 parts of the data pipelines, which is like typical data pipeline. Let's say if your data storage is Hive or SQL, any kind of a SQL database, one, you write a couple of queries and put it in a script, and then you execute those queries. And then if you have some kind of a customized use case to further transform the data further, which cannot be done by inbuilt UDF, you write the UDFs yourself in either Python or in Java or in Scala or whatever language you write, and then you make sure that okay, you create the jar and make those UDF available to all your jobs. So that is a separate code that you have to write. Then you write a custom code to put all those together, which is the Hive script, UDFs and everything into the same code so that you can run those together. And then you need a driver code to run your jobs, to schedule your jobs, to run the jobs. So this is the 5 or 6 step process. So now you think about the complexity of this piece, because now you have to maintain the Hive scripts or the SQL script. You have to maintain the UDF code. You have to maintain the custom code and the driver code, and you have to maintain the wrapper. So there are so many pieces. Some people write in Python, some people write in Java, so you have to maintain all those to actually run a job. So a job contains so many pieces. So once you have a job numbers in hundreds, like we have at least 400 to 500 jobs that we run at a time, think about that, how much code it generates, and we have to maintain all that code. So I was in the starting, when everything was going out of control, I was figuring out how to manage all these things. In fact, I was thinking of writing like kind of a customized pig version where you can write everything in the same script, until I started using the DataFrames. So you can solve, so basically the issue here is that there is no single unified language to build the data pipeline. It's all scattered language. You pull them together, consolidate, and run it across. And there is no easier way to use. For example, like we have, as we mentioned in the previous slides, that we pull the data from the various sources, which is the merchant data, availability data, pricing data, and all kind of data. But the context is almost same, that the data is there in some source. We copy the data across our data warehouse, and within the cluster, we have multiple clusters of the Hadoop clusters. We just migrate the data here and there. So it's just a data copy and data migration. But there is no easy way to generalize your job so that you can migrate the data. It's a single job that can be reused again and again to copy and recopy the data. So there is no easy templating version of the code. So this is how you do it in DataFrames. So in the DataFrames, it's a one single script or the code where you write everything. which is you write your SQL there, you write your UDF. If suppose if you want to transform the data in a custom way, you can write it there only. Then you have custom code that is also there, and then the driver, everything in together at the one place. So this is, I'll show you an example of one data science code, k-mean clustering, which is to determine the query, to put the queries in the 3 different buckets. What are my top queries at one point of time, what are my tail queries, and what are my median queries. So currently it's written in the Python, and it is close to 500 to 1,000 lines of code, and this is the old version of the code that looks like. So if you look here, so here you see there is a pre-process step where you put all your Hive script and everything, which you use to transform and massage the data. And then there is a process step, which actually does the feature extraction of the data, which extract the feature from the transform output. And then there is a post-process, which uses those features to train your model, k-mean clustering. And then there is a final step, which actually take everything and put it in the, denormalize the data and put it into the Hive so that people can use the data. Now think this is the code that we have to maintain. This is the version of shell script, Hive script, Python, and inbuilt the Java UDF, which jar that we pull dynamically. So there are so many pieces that you have to take care of it. And in the UDF world, so many people develop the UDFs. Like we have close to 200 custom UDFs that we take care of on a daily basis, other than the UDF that which we pull it from the open source. So on that way, if you look at it, that if one person screw up the UDF, that means that all our data pipelines which uses that same common jar breaks. So this is the code. This is the same code for the k-mean clustering. It's a modified version of the code for the presentation I just did. But if you look at this piece of the code, you parameterize everything in the starting. Then this is the query, which is kind of a very parameterized version of the query, which we can use and reuse as and when people use. So basically it's kind of a templatization. So basically this query gets built on the dynamic fashion, and then you execute this query, and then I cache the intermediate results. So one more good part about the data frame, which I realized while using extensively, is that if you run Hive query or the pig query, you can control on the performance up to very limited control. You can do the inner join or hash join, map join and everything, but you cannot control the output that much if you further want to tune the query. But here, since you are controlling each and every step, I can even cache whatever I want to cache, whichever step I want to cache, and reuse further later and tune my performance the way I want to tune. So I cache the result, then I have the UDF, which further complex JSON, transform the complex JSON into the simplified version, and then I train the model here, which is I'm training the model. And this is my post processes where I just denormalize everything and put it into a Hive so that people can use it. Now think about this code. The Python code or the code that I showed you that contains 500 to 1,000 lines of the code, this is hardly less than 100 lines of the code. And this is the Scala basically. You can do the same thing in the PySpark or the Python version also. And think about it that one more flexibility, those who are passionate about the object-oriented version or something, they can write the same thing in the object-oriented way. But then I feel that you don't have to, because data pipeline generally you write in a scripting way. So I just wrote it in the scripting way. This is a one single script which does everything and which does all the steps. Next thing is, so this is the k-mean clustering. Next thing is the anomaly framework that we developed, which is extensively uses the data framework. And the requirement that was given to me is that, okay, how can we detect the issues upfront before anything goes to the indexes? Let's say if some wrong image goes to the index, and some customer or the business detects, okay, this image is wrong, by the time we are already late because it's already there in the index. We figure out, okay, where exactly the issue happened, and then we reprocess everything and just put the correct image. So basically to figure out on the upfront how to detect the issues, how those issues correlate to and can impact my output, final output. So for that, the basic requirement is everybody has to use the same framework in all the pipelines and all the alerts or all the issues go to the same bucket, so that you can run some models and correlate what are the issues on the source data can cause and impact the target. So that means you have to develop some kind of a lightweight framework so that people, even the people who doesn't even know the code and the SQL or anything, they can also use. So this is a general architecture. I'll not go into the Anomaly framework architecture because the intention is to show you how to use the framework. So think about this thing. This is what we ask. If somebody wants to run a query and do the anomaly detection on the query, they can write the query. Somebody wants to check the detect files, they can just give the path of the file. Somebody wants command line, they can just give the command line. And the anomaly framework detects everything, takes everything, and just train the model offline. And next time when you use, and it is an API version, so you can use an API anywhere in your data pipeline. Whenever your output comes, you call the API, get the output into the API, and it tells you, okay, whether the data that you are giving me is anomalous or not. And based on that, you can act whatever you want to act. And since we are storing all the outputs and everything internally, in the end, we run a couple of models to correlate. Okay, today's issues are there. Those are the issues in these different pipelines. What could be the impact of those issues on my final version of the output in the index? We have most of the, at least the data pipeline that I own, which already plugged into this framework, but we are plugging everybody else's pipelines also so that we can do the fair cause and effect analysis. So this is for all those people who doesn't know any coding. They can even define the data in the way, okay, this is what my table is. I want to track the metrics, which is the count, sum, average, whatever the metrics. There are 15 different metrics. They can choose whatever metrics they want to track, what date on data they want to do. We using the data frames. So this is how the data frame works. We take that output based on the whatever the metrics they want to track. We dynamically figure out, okay, this guy wants to track the count or the sum or the average of an output on the daily basis, and this is just a snippet of the code that does all those things and just process the data. And as and when it sees the anomalous data, it just trigger a mail and generate the report in the end that, okay, these are the data sources and those are the issues that we detected. And these are, so basically, this is the case for basically if there is any table or any particular column that you want to track on the daily basis, which you think that is important to track, you can define here. But if, let's say, you want to define, you want to track a file, so you can give the file path, which is, okay, my file version is the HDFS version, S3 version or Hadoop version, this is my file. If you look at the latest partition, date -10, you just define your partition. We internally figure out that what partition you want to do, that you, on the daily basis, you want to track the 10th partition of the data, and we track all those things. If, similarly, if let's say if somebody wants, especially our DevOps, they don't do, code or anything, so what they want to track is, they fire a couple of commands to track, okay, size of the file or any command. So you can put that command also here. We'll fire the command on the back end and track the result on the daily basis. And on the weekends, right now all the models are offline models, and right now we have time series models that we run on the weekly basis to train the output and make the results available. If you have a SQL, you can just write the SQL directly here, plug the SQL, it will start tracking the SQL as well. So this is the code snippet basically for the file processing. So the way we do is that, okay, we say, okay, the output is the Hadoop output, and you want to track the size, this is the code. If you want to track the file count, this is the code. If you want to track the directory count, this is the code. Similarly, the local file version of the code as well. So same thing that we track on the daily basis. So the good portion is, good part about this thing is, so right now, initially we had some version of the Anomaly framework, but the thing is that everybody was doing in their own way, alerting and detecting issues. So there was no way to figure out that, okay, who is doing what. So we developed this framework, and now it's an API, basically a very lightweight API, which you can use in your code or in the job, in the final output. And the same API can be used by the streaming pipeline also, online streaming pipeline, so that we can track the issues upfront. And so finally, I would like to conclude here. saying that, okay, the reason we chose data framework, again, for the data frameworks to work effectively, it has to be, it's not, I mean, you have to do some work at least, because I started using the data framework when Spark 1.1, at that time it was a lot of work because it was not tuned properly. But after Spark 1.6, data frames was stabilized a lot, and you still need to do some kind of a tuning. But once you do the tuning, they works very well, and then you can generalize and you can build the template that I show just now. So similarly, for all our ETL jobs, we build a couple of templates, especially to source the data. People they don't have to write the code or anything, just modify the template and plug it in, and it internally generate all the required queries and everything. Using the data frame, we pull the data across, whether the data across from the different source to our data warehouse, whether within our data warehouse from one cluster to another, everything. Now we do it with the data framework. So basically the conclusion, I think, is it's a single consolidated data engineering language, I feel. Rather than you are having code snippet everywhere, you can build a generic language, use as a generic data engineering language, and you can use it. It's very easy to reuse the code. Generally, the one I showed is like you can build the templates and you can reuse as much as possible. Also, you can tune each and every step because it gives you a flexibility to do whatever you want to do at each and every step. And in the last, the better code maintainability. Now, the code size, as and when we are using more and more, the code size is getting reduced and reduced rather than increasing, because it's the one single code that we try to reuse as much as possible. So, thanks. And if you have any questions or anything, you can shoot me a mail or a Jan a mail, or if you have a question right now.
If I may ask, if someone is new to microservices and new to Spark Streaming, are there things they should look out for, particularly in terms of performance?
If you are new to Spark, so the question is, if you are new to Spark ecosystem and the microservices, what are the performance things that you should look out for? If you are new, to be very honest, you will be, first time when you're going to use, the first message that you're going to get is the memory issues. That is typical for the Spark. But then again, you have to at least have some basic knowledge to tune. Spark is like, for example, it's Hive and everything. If you know the query, you just write your queries, correct? It will give you the result back, even though it can be further tuned to run the same queries in 5 minutes rather than 5 hours. But with the Spark, the case is different. With the Spark, if you fire the query, after 5 minutes, it will fail if you don't tune, if you don't run it with optimally. And I think I heard that after Spark 2.0, they got stabilized a lot. I haven't played with the Spark 2.0, but yes, I think to play with the Spark, at least in terms of the performance, you have to have some kind of a basic knowledge, based on my experience. Yeah.
You mentioned that you had to tune the data frames. Do you still have to do with the latest versions?
So the question is that whether we had to tune the data frames. The answer is no. So the thing is, in the data frames now, there you have specifically, if you know what you want, if the data size is, the thing is that if the data size is small, you don't have to do anything. It works like a charm. The problems happen, based on my experience, the problem in the Spark happens when the data size grows beyond a point. That's when it started giving error. And the thing is that the type of error it gives, it doesn't give a very specific error, it fails, correct? So, but there are tweaks, correct? So like, for example, very small, like group by, correct? So if you do the group by key, it works like great. But if you simply use the group by in the Spark data frame, the same thing that works in the 5 minutes may take hours, correct? Error may fail. So the hooks are already there. It just, you need to know what hooks to apply. And if it is, the data size is again small, all the hooks will work. All those tuning stuff comes when the data size grows beyond a point. So yes, I don't have to tune, but yes, sometimes the data frames did not work. I had to write my UDFs. But again, it's very easy to write in data frames. So.
Hi, I have a question about caching, sort of like along the line of performance or tuning. In one of the code samples, you showed that you cached the RDD in its entirety, just .cache. But have you considered when the memory is not big enough,
Yes.
You should use, say, a hybrid caching, say, memory and storage, right? So what were the issues you encountered when you tried to cache the whole thing and you run out of memory? Thank you.
It's the same answer. It's all that when the data size is small, everything works like a charm, which is like caching also. So the good part is that even if you look at the non-data frame version or any other things, the data gets cached and non-cache. Mostly it doesn't get cached, so the performance get impacted. But if you have so many small data set, it's easy to cache in the Spark. You can mention easy to cache. Even though if you don't want to cache, you can put it in the disk. But the thing is, if the data grows, so the way I do it or we do it, if the data, we know that okay, the data size grows beyond a point, we instead of cache, we just write to the disk, or sometimes disk plus cache. Both options are available in the data frames. I mean in the Spark. So again, the cache is the local cache, correct? So you can build the compute node, you can elastically increase the compute node. Yes, if you have more cache nodes, you can elastically add. But again, it's a one single cluster. So the executor, it allocates the executor based on the memory. So let's say that some machines have a less memory at the time of launching an executor. If you have some machine with the bigger cache, it allocates the executor there. So yes and no. You cannot do it while running. But once you restart, you can elastically add more nodes with a better cache and run it.
Okay, we're out of time for questions. Thank you very much to the speakers. The next session, or the next talk will begin at 11:40.
Thank you, everybody.